So good afternoon and welcome everyone to the Barcelona Mathematics and Machine Learning Colloquium Series. This is an activity organized by the University Autónoma of Barcelona, but we do it having in mind all the other institutions in Barcelona, and we would like to share our experience with all the people who were interested in it. And very quickly, this is an activity that is trying to answer what are the mathematics behind machine learning and what can machine learning do for mathematicians. We do it 3 times a year, and you can see more details on our website. And we have a talk plus discussion time. As I said, questions are welcome anytime, but you can also wait for the discussion at the end and speak at large. And the most important bit of our activity is actually who. Last year we had 3 great speakers, and this year we have 3 even greater speakers. And today is the turn of Gitta Kutyniok from LMU Munich. And Gitta did her PhD thesis on time frequency analysis on locally compact groups. So yeah, she was doing kind of a harmonic analysis, and her career evolved in such a way that actually she's today a fellow of both CIAM and the IEEE. And she's the head of the Bavarian AI Chair for Mathematical Foundations of Artificial Intelligence, and she leads this group at the LMU Munich, and she will talk today about reliability of artificial intelligence, chances and challenges. So please, Gitta, the floor is yours.
Yeah, thank you so very much, Roberto. I mean, it's a real great pleasure and honor for me to give a talk in this great series. So let me start by sharing my screen. Yeah, so I hope you can all see this. Yeah, I think we all know how tremendously successful AI is these days, but I think we are also aware that there are still major problems concerning reliability worldwide. And so the mathematical angle is extremely important for improving reliability of AI. There are great challenges, but also even greater chances. And so in this talk, I would like to take you on a tour through this area of reliability of AI from a mathematical perspective and discuss with you some chances and also some challenges. Yeah, I think if you look around us, we realize that we are actually at the beginning of the 4th industrial revolution. Our society will change in a radical manner in its full breadth through AI. I mean, we see some instances now, self-driving cars, telecommunication. Also, in certain countries worldwide, legal issues are already to a certain extent decided by AI approaches, and then certainly the whole healthcare sector, be it diagnosis, be it medical imaging, is already governed by AI approaches. On the other hand, I mean, there are a lot of people who are very cautious, and there was a very interesting incident, which is now already a long time ago, 5 years ago. There was a big AI conference, and one of the researchers, Ali Hakimi, won an award. And in his plenary speech, he said, machine learning and so AI is still at the level of alchemy. He said, researchers do not know why some algorithms work and others don't, nor do they have rigorous criteria for choosing one AI architecture over another. Yeah, and so this raised a big discussion, and we worked hard on foundations, theoretical foundations in this respect. We are now 5 years later, but I think there is still a long way ahead of us, because I'm sure you know, if you train, for instance, neural networks, it's still a lot of trial and error to find the best architecture, to see how many layers to take, and so on and so on. So there are, I mean, major parts where we need mathematical foundations still missing. And so now if you look a bit closer, we realize that there are also indeed problems for AI-based approaches, in particular concerning reliability. So for instance, there are problems with safety. There were already various accidents involving robots, and after all, a self-driving car is nothing else than a robot. There are problems with security. One can hack into self-driving cars, also into hospital systems, take over control, modifying maybe data slightly so that the AI makes radically wrong decisions, but a human would not even recognize it. There are problems with privacy. These methods are very data hungry. And we also know worldwide privacy violations happen on a daily basis, in particular in the healthcare sector. And then last but not least, I would say problems with responsibility. Many of these decisions are black box decisions, and also often decisions are biased. So in that sense, I think it's fair to say that one current major problem worldwide is the lack of reliability of AI technology. Now, on the other hand, I mean, politics was not sleeping. So they are on their way to tackle this problem. There's, for instance, concerning the European Union, the AI Act, which is one of the first worldwide regulations of AI, and also the G7, when they met in Japan last year in May, they started the AI Hiroshima process, also aiming for worldwide guidelines concerning AI and concerning reliability. Now, how do you achieve reliability? Well, I mean, I think we agree that what we require is a very deep mathematical understanding. Otherwise, there will never be true reliability. We need to understand things in its depth. And so, as said, I would like to take you on a tour from my perspective. And for that, I mean, to bring everyone on the same level, let me just give a very gentle introduction into AI. And here I would like to focus on the workhorse of AI, which are deep neural networks. So deep neural networks are nothing new. They were introduced by McCulloch and Pitts in 1943. And what they aimed to do was they aimed to develop an algorithmic approach to learning. And since we humans believe we are very good at learning, what they did was they mimic the human brain. And the human brain, we remember from our biology class, consists of neurons which are interconnected. So what they did was they introduced an artificial neuron and then connected those. And so let me just in a nutshell show you if you haven't seen that yet. So a neuron acts like this. We have here some inputs, electrical signals, x1, x2, x3, and so on. They move through these dendrites and might be amplified. This is mimicked by these and modeled by the weights. Everything arrives in the soma. There, everything is summed. And then the neuron needs to decide whether to fire or not, and it does so. And that's the mathematical model for it here by a bias term. And depending on whether the sum is greater than b or less than b, it fires a 1 or a 0. So very simplistic model for a neuron. Now, what you then do, if you train the neural network, you train the weights and the bias terms. So these are the three parameters. And now we can make this a bit more mathematically precise. So an artificial neuron with weights W1 to Wn, a bias term B, and an activation function rho, which is univariate. It's defined as this function. Yeah, and you see that's exactly what you saw on the previous slide. Only here, now we have the more flexibility with the activation function, and we can choose it not only as the Heaviside function like it was done on the previous slide, but for instance, also it could be the sigmoid function, it could be the ReLU, which is typically what is done these days. So that's the max of 0 and x. Okay, so now, I mean, these artificial neurons are connected. You see this here leading to a neural network. And so here you see a connection of all these artificial neurons. So these yellow parts, they have some input here and some output. And this is encoded in the following way. We have here the input neurons, X. Then these connections are encoded by this weight matrix. You see the first output here is this weight times x1 plus this weight times x2. So these are these connections. The second component is this weight times x3, which is this connection. And the third is this weight times x3, which is this connection. Then in here, we apply the bias term B1. We also apply the activation function. And then we keep going. So the next connections are encoded by this matrix and so on. And so what you observe here is that the neural network is a highly structured mathematical function. It's a composition of affine linear maps and activation functions. And so this then leads to this very classical definition of a deep neural network, which you see here, a connection of affine linear terms and univariate activation functions applied component-wise. And one key aspect of such a neural network is also in particular the number of layers, which coincides here with the number of affine linear terms. Okay, so now the question is, what are the key mathematical directions or the key mathematical questions we have to ask? And for this, I would like to take you once through a workflow of how you apply neural networks and then the mathematical questions will come up in a very natural manner. So how do you apply neural networks? Well, they, are there for approximating functions or also distributions. And what we just have at hand are sample values. Yes, we have our sample values, xi, f of xi, of a function. And this function might be very complicated. It might be defined on a lower dimensional manifold, and it might be a classification function. Yeah, so here you see an image. Computer scientists like to separate cats from dogs. So here, the sample values would be images, and the function values would be, well, 1 or 2. Now, the sample values will then split into a training and a test data set. The test data set you set aside for later use. And the next thing you have to decide now, and this also relates to what I said before, is the architecture. And so there you have to make a lot of decisions. You have to decide how many layers to take, how many neurons in each layer, which activation function. You often certainly do not want to train a fully connected network. So that means you need to set already some entries of these weight matrices at this point equal to 0 and so on. Once you've decided that, then you need to train. And training means learning these affine linear functions, so learning the weight matrices and the bias terms. This you do typically by an optimization problem. You see you have here the neural network function, dependent on the weight matrices and biases. You apply it to the sample values, and you would like that this is close to the true function values which you know. The closeness is given by a loss function, maybe the square loss, and then you sum over all training samples. And maybe, if you want, you sometimes also have a regularization term, which I did not put here. The optimization then is done via stochastic gradient descent, because gradient descent would not work since your training samples are in the millions and you cannot compute for each iteration 1 million gradients. So therefore, stochastic gradient descent, which in each iteration just uses a random selection of samples and just computes the gradient for those, assuming that this gives you a good average. Once you've trained the neural network, everything is fixed, and now you can test it. You now take your test data set, which it has not seen before. You apply your neural network to it and hope that then also the correct function values are computed. So this leads to the following research questions. The first, what we did was we selected an architecture. And this is the first research direction. It's called expressivity. So as a mathematician, we would say approximation power. This asks the question which architecture to choose, which approximates the correct function spaces. And this uses a lot of applied harmonic analysis, approximation theory, and so on. The second is learning. So the problem is highly non-convex. Still, stochastic gradient descent converges to good local minima. And so the question is why? And here, typically, tools come from optimal control, optimization, but also, I might say, a bit exotic areas like algebraic differential geometry to understand the shape of the energy landscape. And then some people call it the holy grail of neural networks, generalization. Can we give success guarantees for the overall performance, for the performance also on the test data set? And this usually uses probabilistic statistical tools. So these are all research questions which analyze the training process, the setting up of the neural network, and then the performance of it. There's another direction which is also extremely important, which is explainability. This has a bit different focus. So here you already have a neural network. You don't know how it was trained, but you want to analyze how it reaches decisions. And if you look, for instance, at the EU AI Act, there's the right to explain. So every AI technology needs to have explainability algorithms associated with it. And so this usually often uses information theory, uncertainty quantification, and so on. And then, maybe as the last point, something which I find often neglected is because this is not a Swiss Army knife. Deep neural networks have limitations. So the question is, are there actually fundamental limitations and how do we overcome them? And from my perspective, this is a question which needs to be asked, but which is often neglected at present. And so now I would like to delve a little deeper into some of those topics. I would like to show you some results in generalization, because I think this is one of the key directions, a bit of explainability, and also we'll discuss a bit of limitations. So let's start with generalization. And this is a very classical figure, which you might have already seen in some talks. It is a so-called double descent curve, and it shows why classical tools do not explain what we see today. So what you see here on the left-hand side is statistical learning theory. So you have the capacity of the hypothesis class, so the size of the neural network in our case, and the error. And the training error goes down as the capacity, as the size of the neural network increases, which makes a lot of sense because you can fit the data better. But then the test error after some point goes up again. And this is this phenomena of overfitting, which you see here. So what happens is, for instance, if you would like to separate here these blue stars from the green dots, if your network is not expressive enough, maybe you can only draw a line that's underfitting. If it's a bit more expressive, maybe it draws an ellipse like this, which seems to be quite good because this green dot seems to be an outlier. But then if the network is too expressive and it wants to do the job too good, you run into these problems that it aims to enclose the data too accurately. Yeah, and so this leads to the fact that then, new points might be misclassified, and that's called overfitting. And so this is why the test error here goes up. This is very well explained, but what we observe today is this figure. You see the left-hand side coincides with this, but then after some point, this test error again goes down. So in that sense, the larger the better for neural networks, and therefore practitioners also say, well, if you choose a neural network, choose the largest which still fits in your GPU. And so this is something which is not completely explained at this point. There are a lot of tools which people aim to use, so-called VC dimension, Rademacher complexity, also so-called neural tangent kernels, and so on and so on. And so in this talk, I would like to show you one result which we achieved, which solves one sub-problem completely. And for this, I would like to take you into a world of neural networks, which is extremely hot these days, which are graph neural networks. Yeah, so graph neural networks, in contrast to normal neural networks, operate on graphs. And certainly Euclidean data you can view as a graph. So this is a generalization of normal neural networks. So graph neural networks has F as input graph signals, and the graph signal are graph nodes, where for each node we have allocated a feature vector. So these are graphs which you see here. You have a graph, and at each node you have a feature vector. And so these graph neural networks or convolutional neural networks take this as input. They do convolution, which is the weight matrix. Since we have a convolutional neural network, we activating as an activation function. And then, as it is custom, if the weight matrix is a convolution matrix, one needs to compress again, because otherwise the dimension becomes too large, one pools, and so on. So this is how the sequence goes. And these are extremely popular because they have a lot of applications. So for instance, recommender systems, fake news detection, chemistry, for instance, molecules are nothing else than graphs, and so on. So there are also now their own conferences concerning graph neural networks. Okay, so now let's come to generalization in this field. And again, what we aim to do, and this is a generalization question, we aim to ask, or we ask whether a graph neural network or a graph convolutional network behaves in a correct manner on graphs which are not in the training set. Yeah, so how does it perform on out-of-sample data? Yeah, so let's assume, I don't know, the right-hand graph here was in the training data set, but now we put in the left-hand graph and we ask whether it has, whether it correctly maybe classifies it. But here in this realm, we now have a sub-question we can ask, because you see, graphs can look alike. They can model, and we will make this precise, the same phenomena. So which you see here, they look a bit similar. And now we can ask this general question for this situation. So let's assume from this class I have one of the graphs in my training data set, does then the neural network behave in a benign manner afterwards on a graph which is in the test data set, but which models the same phenomena? Yeah, so this is a sub-question which you cannot ask in the Euclidean set, because there, I mean, this modeling the same phenomena does not make any sense. Okay, and what we can show, and what I will show you now, is that we can prove this transferability, so that if a neural network has this, for instance, as an input graph, as a training graph, that it is able, after training, to transfer to graphs which model the same phenomena. I will show this to you, that we can do that for graph neural networks with particular convolution filters. Okay, so let's first define convolutions on graphs. Also beautiful theory by its own. Let's assume I have the degree matrix and the adjacency matrix of my input graph. Then I can define the graph Laplacian just as the difference, and I can also normalize it. Now this graph Laplacian is a self-adjoint operator. It has eigenvalues and eigenvectors, and it encapsulates the geometry of the graph. So what you see here are the eigenvectors. Yeah, so this is drawn in a smooth manner so that you can see it a bit better. But what you see here is that indeed, I mean, it has different frequencies, and in fact, according to the structure of this graph. So this bottleneck here, I mean, there you first have the frequencies just going through the bottleneck and so on and so on. Now, so the graph Laplacian is a very well known concept in graph theory. But you can use it to define convolution on graphs. And you do that in the following way. If the uj are eigenvectors of the graph Laplacian, then the convolution operator is defined in this manner. So here you have the convolution coefficients. Here you have your input, f, and then you compute this spectral decomposition. Yeah, so this is the classical spectral graph convolution operator. Yeah, so it's associated with these filters, so you can change it by modifying the filter, a discrete filter. Now, if you define your convolutions in your graph convolutional neural network this way, you actually have a huge problem, because first of all, computing the eigenvectors is extremely time consuming, and often if you have large graphs, you cannot even do that. Also, you don't have a fast Fourier transform on graphs, which you actually would need to compute, for instance, terms of this in a fast manner, because then typically you compute it in the Fourier domain. But even worse, if you define convolutions this way, this will not be transferable. Since let's assume you have a graph which you modify slightly, then the eigenvectors might change a lot. And since this is always fixed, the convolution operator will change a lot. Yeah, so therefore, this will never work. So you have to do something a bit smarter. And here we, again, look into mathematics and consider functional calculus, which is a very exciting topic in functional analysis. So functional calculus, I'm sure most of you know, but for those who don't, functional calculus aims to, if we have a self-adjoint operator, to apply functions to it. Now, so if g is, for instance, a square function, this would be t squared. Now, so that would be easy. But g can be also the cosine function and something like this. So then it's in fact not that clear what applying a function to an operator actually means at all. Now, but there's a beautiful theory in functional calculus which explains this. And so here in a nutshell, you see that you have, for the self-adjoint operator, you have a classical decomposition formula. And you can do the same then for this new operator, which is a function applied to this operator. So this is a new operator, but again, you have a decomposition of this type. And if g, in addition, is a rational function, then you can write down g of t precisely. Yeah, so I already said if g is just the square function, this would be t squared. But if it's a rational function, you can also just plug in your operator here, and then g of t is just this term. Now you don't even need then here eigenvectors to compute. Okay, so now the trick, and I think this is also a general concept in mathematics, often in the discrete world things are harder. But then if you go to the continuous world, things become sometimes a bit easier and a bit more elegant. And so this is now what we do here. Remember, previously we had the convolution depending on this discrete sequence. So these were the filters. But now what we do is the convolution, the filter of a convolution is not a discrete sequence, but it's a function, it's a continuum object, this G. Yeah, so instead here of modifying this filter, we now have this function at hand. And so then, I mean, the convolution looks like this. It's just this formula. Where now you can modify the G. And this solves all our problems because so if now, I mean, you have a graph and you modify it and these eigenvectors change a lot, then here you still have the eigenvalues and they counterbalance it. So then this becomes actually stable under graph perturbations. And also you solve the computational problem, since if G is a rational function, you don't even need to compute the eigenvectors. So you can just write it down precisely as we saw on the previous slide. So now these are the filters which we use in our graph convolutional neural network. Okay, so what is modeling the same phenomena? So this I kept under the rugs up to now. So if we have graphs, so we have the points of the graph, and we have the strengths of the correspondence between those. This corresponds nicely with what metric spaces are. Metric spaces also consist of points and then of distances between the points. And so now we can do the following. We can say graphs represent the same phenomena if they are discretizations of the same metric space. And so the correspondence now is if the distance between points in the metric space goes up, then the edge weight will go down. So we can view then a graph as a very canonical discretization of a metric space where the weights then are exactly the difference, the distances in the metric space, and correspond to it then. Okay, so this is what graph modeling the same phenomena means. I mean, there are also a lot of other ways to do that. There is the notion of graphones, which is like a limit object of graphs. And you can say if two graphs are from the same sequence converging to a graphone, then they model the same phenomena and so on and so on. So there are a lot of other ways to do that. Okay, so now, I mean, what we want to do is we have a graph convolutional neural network, or maybe just one filter of it, and we want to input two different graphs which model the same phenomena, and we want that the repercussion then is the same. And so this is now the situation. I have two graphs which model the same phenomena, and I want to put it not through the whole graph neural network, but just through one filter for now. Okay, so how do we compare this? First of all, we go to the continuous space, the continuous metric space which overlays it, and take a function on there. Then we bring the function now down to the graph. So we sample it. Now we need to apply the filter to it. And remember, applying the filter depends now on the function g applied to the graph Laplacian. And applying it to the graph Laplacian will naturally link it to these two graphs. So I now apply g, the same g, but with a different graph Laplacians to adapt it to these two different graph structures. Okay, this gives me functions, and now I need to compare it. So what I do for that is I again upsample it, I bring it back to the continuous space, and now I can compare it. And so this is now what I do if I move my two different graphs which model the same phenomena through my graph neural network. And this is what happens just as one particular filter. But now we have all these different layers and so on and so on, and need to compare it. Okay, so we have a very nice estimate for these errors, and let me walk you through that. So this is a general setting which we consider now. I mean, now we consider Borel spaces. This is the analog domain with Laplacians. We have our discrete world. These are graphs with graph Laplacians. Then in the analog and the continuum domain, we take Pali-Wiener spaces, which are band-limited spaces. We have sampling operators, which from the Pali-Wiener space brings it down on the graph, and interpolation operators, which bring it back up on the Pali-Wiener space. And so the error which we will observe is the following. So what you see here is you have here the signal, you sample it, you filter it, and you bring it back up. And first we compare it not to a different graphs, but we just compare what happens if we just stick to the continuum set. Yeah, I mean, then the error is the transferability error of the Laplacian. So here F is just the identity. And the consistency error, which means that the signal is just upsampled, just sampled and reconstructed. So this is just a sampling density, basically, of the graph with respect to the continuous space. And so then, I mean, this is the result in its full glory. What you see here, this is the transferability of one filter. Exactly what you saw on the previous slide. Not only now you have, let's say, all different details, and you see here these two components: transferability error of the Laplacian and the consistency error with some constants. Yeah, so this happens for one filter, and it happens just on one side. We compare if we move one graph through the network and compare it with if we just stick to the continuum setting. Now we put all the pieces together, and then you get this result. So you have now your two graphs with the graph Laplacians, which you move through the graph neural network. You have certain conditions which you need to fulfill, which relates to the fact that we want to apply the previous result. And then this is the error. When we have these two different graphs, we move it to the convolutional neural network, and this is the error which we get. And what you observe here is the number of layers plays a role. This is the Lipschitz constant, the dimension of the Pali-Wiener space, and here this delta, which controls the error on every layer. Now, but you have a very precise result now, and you have a very precise generalization estimate. So in that sense, you can solve and get your hand on this generalization question completely. Okay, so this was one tour into the area of generalization. And I showed you one particular result in the setting of graph neural networks, which you can solve completely and where you can get very precise error estimates. So let's now delve into the second area, which is explainability, which I think, from my viewpoint, requires a lot more mathematics. And here I would like to show you one approach, which is based on applied harmonic analysis, an area I actually work on now basically all my life in a certain sense. So what is explainability in a nutshell? I mean, so let's assume I have a 3 and I pass it through a neural network, and it correctly classifies this as a 3. And then these explainability approaches typically put a heat map on this input. Which indicates, for instance, here that these openings are red. That means that the network looked a lot at the openings to decide that this is a 3. And these blue parts play against it. So basically, this indicates which are the most important pixels for the neural network for that decision. And if this would be classified as a 3, then the explanation could be, well, I mean, the neural network looked at these openings, it played against it, but still it decided that this is an 8. So these heat maps or feature maps indicate nicely what pixels are important, but I mean, from a mathematical viewpoint, what exactly is relevance, what is also optimality, can we use it also for different modalities. And the vision is ultimately that you want to communicate with an AI like you do with a human for the reason of a decision. And also, I should say, I mean, what is also, I think, important, because this right to explain is a legal requirement. So these explainability approaches themselves need also to be reliable. I mean, we cannot only use it for reliability, but then it needs to be reliable, so it needs to be grounded in mathematics. And so let me show you one, for instance, one approach which we introduced. So this is based on information theory and rate distortion theory. And basically we use, I'll explain to you in a moment, we use this rate distortion framework and view it as a framework for explainability. Okay, so rate distortion information theory, what is it about? So typically you have two persons. One person, let's say Alice, has a message and she transmits the message to Bob, but she sends only parts of the message at a certain rate. Bob has to decode the message. He will make an error that way because he only got parts of the message. And this error is the distortion. And so certainly what you want is you want to keep the rate small, but also the distortion. So it's a trade-off. Now, we can phrase this explainability question now in this framework. Let's say Alice has the neural network and also Bob. And Alice has the original image. She's now allowed to transmit parts of the image to Bob, hopefully the relevant parts. Then Bob needs to bring this back to the image size, otherwise he cannot put it in his neural network. And maybe he obfuscates it by random pixels to not distort the meaning. And so then, he gets an output. And so the rate is now how many pixels are transmitted, and the distortion is here the error. And so the task is again now small rate, concise explanation in that sense, and also small distortion. And so this is the rate distortion function. We want to keep the distortion under control, but also minimize the number of pixels which are relevant. This, if you work on optimization, you will immediately say this you cannot compute. It's a very hard problem. It's so-called NP-PP complete, but you can relax that like you can usually do, which it's very similar, for instance, to the theory of compressed sensing, and minimize this objective function. So you have here the distortion plus lambda times now a relaxed version of this just counting pixels, where here in our place you place a value from 0 to 1 on each pixel and you apply the little L1 norm, because the little L1 norm also promotes sparsity. Okay, so this minimization problem you can now apply, and for instance here you see an image of a dog, and the neural network has correctly classified this as a dog, and here you see from different explainability approaches the explanations where the network looked at to classify this as a dog. And so you see ours is tuned for conciseness, and it shows very nicely that the neural network considered in particular the head of the dog for reaching that decision. And so here you see also a comparison concerning the number of relevant pixels and the error which you make. And so ours behaves in that sense in the best among all of those approaches. But then you can ask, why do you obfuscate this with random pixels? That creates, a very strange looking image. And also, why should explanations be pixel based? Because let's say you want to detect an image of a lake. There, not every pixel will be important, but maybe the shape of the waves. And so what we then did is, we, instead of obfuscating these random pixels, we also used in painting guns generative adversarial networks, which generate more natural looking images. And in here, for the pixel-based explanations, we actually looked at decompositions of images, for instance, in wavelets, in a wavelet transform. And this gave us natural clusters of images, and then the relevance was just put on the coefficients. And so this gives a very nice comparison of this approach, which we have, which we call Cartoon X, and image compression. So image compression, in a nutshell, does the following. We have an input image, we compute the decomposition, we select the largest entries, we set everything else to 0. This gives the high compression rate, and then from the white ones, which is very hard to see here, but from the white pixels, which are actually stored, you reconstruct and you hopefully are close to the input image. On the other hand, this cartoon X, this explainability approach, now does the following. I have an input image, I compute the decomposition into wavelets, let's say. Again, I select the largest entries, but now I replace the others with random noise. And then I reconstruct, and certainly I cannot expect that this is close to my original image. But also that's not what I want. What I want is that if I look through the lens of the neural network, then this is close. Yeah, the distortion has to be small. Yeah, so in that sense, it's of the spirit of image compression. And so here are two examples of how you can apply these methodology. This comes from telecommunication. What you see here is a city map, and the red dots are cell phone users, and the white blob here is a cell tower. And what the network computed is this black and white background, which indicates at each point how strong the signal there is. And now you see something very strange, because you see here you have an area of bad reception. But these people stand right in front of the cell tower. They should have amazing reception. And then you can ask, I mean, with this explainability approach, how did the network compute this area here? And so this is the explanation. This is what the network looked at to create this black area. And indeed, actually, these persons have bad reception. And so what turned out later on was there was actually a building missing in the city map. Yeah, so that way you can also detect whether the network actually did something reasonable, although it might look incorrect. And then maybe something which is also completely incorrect, an adversarial example. So here the network decided that this is a diaper, although it's obviously a man with a dog. And here it decided it's a screw, although it's obviously a man with a sweater. And now I will overlay it with the explanation, and you will see what the network has seen to reach that wrong conclusion. So I will put it on top, and what you see here is now that this looks like a baby, so then a diaper is not that far off, and this looks like a screw. Yeah, so remember this was a sweater. So and this gives you now a sense of what the network has let's say, interpreted, and so then you can correct for it. And so now, I mean, this was based on wavelets. You also use shearlets now and other representation system to get more sophisticated explanations. Okay, so this was a tour into explainability, and so in the last minutes, I would like to now also talk a little bit about limitations. And here, I would like to approach this from the viewpoint of that we compute neural networks and train neural networks right now on digital hardware. Yeah, so we break, although, I mean, the problems are typically of a continuous or continuum nature, we break everything down to zeros and ones. And this will cause some problems. And so there is a beautiful area of computability in computer science, which says the computed problem is one on a digital machine where you can compute things for every accuracy. So you have like a universal approach, which gives you an arbitrary accuracy to a certain degree. And what one can show is that indeed, I mean, for so-called inverse problems, which typically appear in medical imaging, so an inverse problem is a problem where you have a measurement process which you need to invert. So for instance, for a CT scanner, you have the measurement process, and then from the CT measurements, you want to invert and recover the human interior of the human body. And so what one can show is that often the solution of these finite dimensional inverse problem is actually not computable by a deep neural network. So this is not a problem of the task we need to solve, but it's a problem of the hardware. And well, as we know, today computations are performed almost exclusively on digital hardware. And so what this causes is that, I mean, there's no, let's say, universal algorithm which gives you the solution for any given accuracy. We could even show there is often a systematic error larger than the machine error which you obtain. So in that sense, the output is not reliable, and it could point towards why you see these instabilities and non-robustness, because I mean, remember Elon Musk, I mean, spent billions basically for his self-driving cars, but still we are not, by far not at the level what we expected it to be. And it could be a problem of the hardware component used. Then on the other hand, I mean, there's also a way out, which also mathematics shows us. Because we can show that now in the contrast of Turing machines, which is the classical model for digital machines, there are so-called Bloom-Schupf-Smale machines, which are a very classical model for analog machines. Then things become computable. And so that could mean that for certain problem settings, you require novel hardware. And indeed, I mean, there are actually really exciting developments, like you might have heard of neuromorphic computing, biocomputing, quantum computing, the true quantum computing, not with qubits, but the true photonic-based quantum computing, and so on. Yeah, so a lot of different new hardware in the development, and neuromorphic chips already exist, which also actually have a different advantage, because we all know that GPUs are extremely energy hungry, but for instance, neuromorphic chips are much more energy efficient. And so these computability problems we could actually show for many instances, classification problems, or the pseudo-inverse, and so on and so on. So it could be that if you want to have, let's say, provably reliable AI, that you might need to augment the digital hardware in a certain manner by the digital hardware in a certain manner by analog computing, analog. Okay, so let me conclude with some final thoughts. From my viewpoint, I mean, we live in really exciting times. I mean, AI shows great promise, as said. I mean, it will change our society, it will change industry, it will change science in a radical manner. But at the same time, I mean, we are still missing this strong mathematical foundation, which we need for reliability, and which also for legal requirements we require. And then, I mean, I showed you what I believe are key, let's say, mathematical directions which need to be pursued: expressivity, learning, generalization, explainability. We took a bit deeper tour into generalization, explainability, and then also discussed a bit of limitations from a computability viewpoint, which shows that indeed one might need to reconsider in certain instances which hardware is used. And so I think in general, I mean, there are really exciting future perspectives from mathematical foundations, and they are also desperately needed for getting true reliability. And let me, before I come to the end, also finish with a short advertisement, because since I talked a lot about reliability, we actually just started basically 2 years ago in Munich, the so-called Konrad Zuse School of Excellence in specifically reliable AI. This is set up between both universities in Munich, the LMU, where I'm at, and the TU Munich. And as you see here, the areas, mathematical algorithmic foundation is one main large research area, next to medicine, healthcare, robotics, interacting systems, algorithmic decision-making, everything intertwined with reliability aspects, safety, security, privacy, and responsibility. And so the idea is to educate master students, PhD students, not only in AI, but also with the awareness of the importance of reliability. And with this, I'd like to conclude, and thanks a lot for your attention.
Okay, so thank you for this very tangible and tactile talk with all the the math inside. So now it's time for questions and discussion. So as you know, you can raise your hand if you have any questions. I may have the first go then. I would like to ask you first if you can comment a bit more on this overfitting versus over parameterization that you mentioned at the beginning. Yeah, because as you said, somehow like the mindset was this, like overfitting was seen as an issue, and then actually you said now you should just put the biggest architecture that you can afford. So can you say a bit more about that?
Yeah, that's a very good question. Yeah, as we see somehow, I mean, this modern regime, the size then seems to overrule the overfitting. And so what theoretical considerations show is that there is some inner regularization happening to a certain extent. Yeah? So once you train with stochastic gradient descent, there seems to be some implicit bias. And there's a whole, let's say, range of theory in generalization to understand this implicit bias, which happened during the training process to prevent overfitting. Yeah, so in that sense, I mean, there seemed to be some smoothing, some clever regularization in an automatic manner happening so that you don't end up with something like this, but you still end up with something.
Is there any dependence on the activation function you are using? Will you say like, okay, you are good to overparameterize as long as you don't do it with this activation function, or actually it's like, no, that doesn't matter what you do, largest is best now?
Well, I mean, activation function, so what is typically used is the ReLU, the rectifiable linear unit, so this spline function, piecewise linear. For some reason, I mean, although it's very simplistic, this seems to be sufficient for practical purposes. I mean, some people sometimes use sigmoid, but I mean, also the theoretical foundations and everything usually focuses on the ReLU. So I don't believe it happens. It has also anything to do with the activation function in that sense. I mean, I think it needs to be something, yeah, something else which happened during the training process.
Okay, so when you spoke about the cartoon X and you put these very nice two images of the diaper and the screw, you said that this will help you correct. So I wanted to ask you, okay, how would now the correction go? Can you tell us about it?
Yeah, also a very good question. So I think you need to find then images which, in a certain sense, augment this problem and fine train it. So what you usually do with a neural network is anyhow, I mean, you first train it with simplistic images and then you fine train it with more sophisticated images. So here you might want to, I mean, retrain it, maybe taking parts of these images out and modifying them so that you prevent it, and maybe you have, so if you want to classify this as a sweater, you might want to use for training purposes images which have a more prominent sweater so that you cannot, or that it cannot be misclassified.
Okay, yeah, but then then it's very specific somehow. I mean, like if you say like, okay, take sweaters and take diapers. Right?
It is very specific, yeah.
Okay.
I mean, but I mean, all the training process and also the explainability, this is at this point, I mean, still very specific. I agree with you. There is a lot still to be done, but I mean, also here for the, let's say, explainability, it's also very much focused on single images in a certain sense.
Okay. And later you mentioned this, when you mention quantum computing, you put there some machines that are like Blam-Shapps-Mail. Could you comment on them? Yeah, this thing. Yeah. What are they? Because I don't know.
So, I mean, let's say we start with a Turing machine. So a Turing machine is a classical model for a digital computer. So you have a tape and you have this head which moves around. So Blam-Shapps-Mail model is a more complicated one, which assumes that you can actually compute also with reals. You have a certain set of operations which you can use. And so in that sense, it is one possibility for an analog machine. It is not clear yet, I mean, how close this Blam-Shapps-Mail machine is, for instance, to neuromorphic machines or to biocomputing. So this is still under investigation to see in which sense or to which extent this can be also maybe even precisely realized in hardware or not, or what is the closest hardware according to this theoretical construct. So right now this is mainly a theoretical framework which needs to be brought into reality, which for the Turing machine is already there because everybody believes that the Turing machine is the correct model for the digital computers which we use currently. Okay.
I wanted to ask you also about like one of the four subjects that you touched less, which is expressivity. I've seen you have like a very nice survey on that, and then yeah, somehow it would be nice if you can very shortly say why or how you prove somehow that deep neural networks, as in having many layers, are better than having many nodes in a single layer. Okay, that is because that's there are some works in this direction. I wonder if you could comment very briefly on that.
Yeah, so okay, so thanks for highlighting our survey article. Yeah, so there are a lot of different approaches to do that. I mean, there is, for instance, work which shows that there are certain functions which you can compute with 3-layer networks, but not with 2. So typically in the area of expressivity, everything is very constructive. So you explicitly construct function classes, or you specifically look at function classes and then construct, let's say, neural networks, let's say, with 3 layers, which can approximate them up to a certain degree, but which is not possible for a two-layer network. And so what makes these networks, I mean, that effective is this, let's say, this layer structure, because it's kind of like a concatenation, which has a huge advantage over also classical approximation theory. So, I mean, right now, also the success of neural networks cannot be explained fully by classical approximation theory, since, I mean, you have this compositional structure. I mean, this is the huge advantage of neural networks. And so therefore, it is also advantageous to have more layers, because then you have more of these concatenated structures, these compositional structures, as opposed to having just more neurons in one layer.
Okay, but I mean, from what I understand, like this, the example you said, 3 against 2, it has to do about like more of asymptotic behavior, because in principle, there are theorems that tell you that even with 1 layer, you can approximate any function to any given like accuracy. You would like, the thing is that the growth of the nodes will be like will be non-poly. I think I don't know if it's non-polynomial. I guess that would make sense. I mean, I'm thinking about this work. The one I have in mind is by Danieli. I think Danieli, where he does it. Yeah. So I also asked you this question because in this part of expressivity, somehow in my mind, there are like these 2 results that help me really shape what's happening there. One of them is actually this thing is Pincus, Lim's column, like saying like we can approximate with neural networks under certain hypothesis any function to any desired accuracy, and then on the other hand, something saying, okay, but actually going deep is better than having many nodes in your, and these are for me are like very mathematical statements. Like I can see them as something purely mathematical, actually, just by thinking of functional analysis, and my class of functions are now like neural networks because they are a class of functions. So I wanted to ask you, with this with this in mind, whether in the other 3 that you told us about, like learning, generalization, explainability, whether you can highlight some results, like saying, okay, like Netflix, if you liked that theorem and you like that other theorem, so you will also like this theorem here.
Oh, I see. Yeah, so for learning, I mean, the learning type mathematics, these are always optimization problems. So, I mean, the results which you there aim for are convergence results. So, what does stochastic gradient descent converge to? What are good starting values? So overall, if you like optimization theory, in any case, you have an algorithm and you would like to compute the convergence rate. I mean, this is basically the essence of learning. Now, generalization is very diverse. I showed you one generalization result, which was a bit non-standard, so that used a lot of functional analysis. But often generalization results are much more from the statistical probabilistic viewpoint. I mean, this whole statistical learning theory, which explains this one first figure, I mean, goes in there. So this is a lot of statistics. And explainability, I mean, this is an area which is very open. And I think it needs a rigorous mathematical foundation. But on the other hand, it's also very difficult, because if you ask yourself, what is a good explanation? This is not even clear. It has a strong social science aspect with it, and a strong also language aspect with it. So in that sense, explainability, it is also not clear to me at this point how mathematical you can actually make this area. So therefore, I mean, saying a result, a key result, I think it's very difficult. But people use, I mean, for instance, also game theory, there are Shapley values, and so on and so on. I mean, so I think explainability is a very diverse area, where people throw all different types of tools, information theory, and so on right now on. And I think it's still on its way to find the heart, the mathematical heart of the area.
Okay, I remember if someone wants to ask a question, of course, you are welcome to do that. Just raise your hand. Okay, yes, okay, winding down now, I have a question, or perhaps the opposite, actually. I wanted to ask you about this EU regulation, because somehow, I mean, to talk about explainability, I mean, explainability is like a very big problem. So I mean, what I've heard is like, okay, we know it works, but how does it work is actually even harder to make it work. And I don't know if you follow the process, perhaps even you took part on it. So how is the feeling of the EU legislators when they ask for something like I guess they rely on experts, of course, but how do you see the process? Because it's a bit tricky, perhaps their understanding. I mean, there are people who are not computer scientists, not mathematicians, and still they have to write the laws. How do you see it?
Yeah, I think that's very difficult. So I mean, from my viewpoint, I think if you look at the formulations, what it needs right now is I might say, mathematization. So I mean, there's a right to explain, and the problem is that everyone can interpret this in their own ways. Yeah, so every industry representative can interpret it in the way which benefits their company. So I think this process is missing. There needs to be something like a mathematization of these legal expressions so that you can then test them and check them in an automatic manner. So in that sense, I think this is what is maybe a huge problem with the EU AI Act, that there is not too much discussion between politicians and, let's say, computer scientists or mathematicians. And so therefore it is, from my viewpoint, it is a good step in the right direction, but it is too vague right now, and there's no possibility basically to check that automatically, and it leaves too much room for interpretations for something which you could actually make much more precise.
But do you think can be done already, with or we are still like we need some more technical or conceptual development until they write something there which is not just a declaration of intentions, but actually that can be checked? How far you think we are to that point?
Well, I think so. So let's also come to the area of explainability. I think there still need to be some research done, because, as I said, I mean, it's not even clear how mathematical explainability can be in the end. On the other hand, if you look, for instance, at privacy, differential privacy, I mean, there is a lot of mathematics involved. So I think it just needs a group of people also sitting together, maybe before they then meet with politicians, and phrase this in much more mathematical terms. But yeah, I think we are not there yet. I mean, there need to be a bit more discussion, but maybe, I don't know, if some projects are formed, maybe in 6 months, 1 year or so, I mean, we can reach that level. But then, I mean, there also need to be that effort to do that. So it's not clear to me whether also politicians are open enough for something like that.
Okay. So let me close by a question about your career, actually, because you started with harmonic analysis. I don't know how somehow it was pure mathematics, so you already saw it was kind of applied mathematics at that point. But I don't know if you envision yourself as in the position you are now, like as chair of this AI group in Munich. So I wonder if you can comment a bit on that, because there are also some fellow mathematicians who are now like early career researchers and may find themselves in similar situations.
Yeah, that's a very good question. So I started actually as a pure mathematician because my supervisor was working in abstract harmonic analysis and group representation theory of locally compact groups. So, but then, I mean, I got hooked a bit, let's say, in the applied direction and moved to applied harmonic analysis, imaging sciences, inverse problems. And then I think it was maybe 8-9 years ago, this deep learning wave hit also the area of imaging sciences. And people needed to orient themselves because these new methods were extremely powerful and easily reached the state of the art. But I mean, all the error bounds which we worked on for a long time before, I mean, they were all thrown overboard. These new methods did not have any mathematical theory, or barely any. And so some people kept with the traditional methods, but I don't know, I got excited and viewed this as a chance. And so then I switched my research. I still work, I mean, one part is still imaging science, is applied harmonic analysis, but I then decided to embrace these new methods and also build, let's say, a new research direction and concerning reliability, expressivity, generalization, and so on. And so I think from my viewpoint, that was one of the best decisions I made in my life, to embrace these new methods, because it's a very exciting time. But on the other hand, it also, it takes a bit of courage, because you need to learn a lot new, which is exciting, but then it takes you a little bit of time again to publish at the rate you published before. But still, I mean, so my advice would be, if there is something like this, new methods come up. I mean, if you don't like the new methods, I mean, don't embrace it. I think one needs to do something which you really, I mean, where your heart is in. But then if you think, I mean, this is an exciting direction, I think it's, yeah, I recommend really to take this step and also embrace new methods and see them as a great chance, because I also saw some colleagues who stick then with the traditional methods, some people who still work on abstract wavelet theory, but these communities become extremely small, and it's also very difficult to get jobs with it and papers accepted and so on. So in that sense, I think not always go with the flow, but if you're excited about it, then maybe embrace the method. Also find your niche in some sense. I mean, it's very difficult to compete with, let's say, the whole world. But view this as a chance. I think, I mean, changing, let's say, the research focus at least once or twice in a career is a very good idea. It's very rewarding and very exciting.
Okay, well, thanks a lot. Thanks for everything. For people who want more, I think you have like a series of lectures on your website. I saw like you were invited as there are like 5 or 6 lectures or more on this topic on videos that I also recommend. So yeah, let me thank you again for the very nice talk and accepting our invitation. And let me just remind the audience that the last talk of this series will be on the 18th of April, and we'll have Yao talking about geometric understanding of deep learning. So that's all on our side. Have a nice week, and thanks a lot for joining and for giving the talk.
Okay, thank you so much. Thank you.
Okay, thank you very much.
Thank you.